the magnetic field due to this vector potential. So we're going to write it down, just this once as H sub A, but in general, for this, because we know we only have an electric current, we're not going to worry about it, is 1 over mu times the curl of A. You can find the electric field directly from A by writing it down like this. E sub A is minus j omega A minus j times 1 over omega mu epsilon, gradient of the divergence of A. Or you can find the electric field from the magnetic field. That's the thing I like to do, because then you just end up doing a curl 2 times, because we remember from Ampere's law that the curl of H is j omega epsilon times E. So either one of these 2 ways are the ways to find the electric field from, if you know either the magnetic field or the magnetic vector potential. What you get after you do that is these are the fields. First, H phi equals 0, which makes sense because since H is the curl of A, H has to be perpendicular to A, and A is phi directed, so there should be no phi component of H. So far so good. Next, we have HR, which is j k little a squared, that's the radius of the loop, remember, I naught cosine theta over 2 pi, oh, not a pi, 2 pi r squared. Look at that 1 over r squared right at the front. So the H sub r term, the r component of the magnetic field, doesn't contribute to the far field radiation, the radiated power or anything. And then we have in parentheses times 1 plus 1 over j k r, another term of 1 over r here. So this has 1 over r squared and 1 over r cubed. And then we have our phase term, e to the minus j k r. So this r component of the magnetic field only contributes to near field. It is the theta component of the magnetic field that has all your far field radiation stuff going on. That one is minus Ka quantity squared I naught sine theta all over 4r, look, that's just 1 over r, times 1 plus 1 over jkr minus 1 over parentheses kr quantity squared, and again with the phase term, e to the minus jkr. So in this one, that term, that little 1 right there, that is the one that carries the far field power. And these other 2 terms are near field terms. What about the electric field? When you work this out, you get that the electric field only has a phi component, which makes sense because as we know, well, never mind. There we go. E phi is eta times Ka quantity squared I naught sine theta over 4r times 1 plus 1 over jkr e to the minus jkr. All right, I wrote these down not because I want you to remember them or write them down yourself. You can always look them up in the book, but I wrote them down because I have said before that loop antennas have an interesting and mysterious equivalency to the infinitesimal magnetic dipole. So I'm going to write down what the fields are for the infinitesimal magnetic dipole, and then we are going to compare them. And actually, since this is a recorded video, I can do magic and you don't have to sit through me writing it all down. I'm going to just write it all down and then, yeah, do it really fast. So we have that ER, E theta, and H phi are all 0. The remaining components are E phi, HR, and H theta. All right, so far so good. The same components exist and don't exist for the infinitesimal magnetic dipole. So that's great. The E phi component is minus JK times the magnetic current times the length of the magnetic dipole sine theta over 4 pi r times 1 plus 1 over jkr e to the minus jkr. The r component of the magnetic field is the magnetic current times the length of the magnetic dipole times cosine theta over 2 pi eta r squared. 1 plus 1 over jkr e to the minus jkr. Lastly, the theta component of H is jk, magnetic current, length of the magnetic dipole, sine theta over 4 pi eta r times 1 plus 1 over jkr minus 1 over kr squared e to the minus jkr. All right, here's how we're going to do this. First of all, look, all of these terms with the r dependence in them are the same. They are exactly the same. Second, the r dependence in these leading terms is also the same. And the angle dependence in these terms is also the same. But we have some differences. The constants on the E phi term, on the leading term, are eta times Ka squared times I naught over 4. So you can see that there's a difference between what I wrote here and that is not circled and what's over here for the infinitesimal magnetic dipole that is not circled. If you go through and compare all of these expressions, what you get is that they are equal if the following condition is true. It's equal if the magnetic dipole moment, Im times its length, is equal to j pi a squared. So that's the area of the loop, which is often just written as S, times omega mu I naught. So cool, a small loop is about the same as an infinitesimal magnetic dipole. And in general, magnetic currents are things that can represent and replace loops when we're doing antenna analysis. I'm going to wrap this up with a few key things about loops. Thing number 1, if you integrate the power density and then you divide by I naught squared, you can get the radiation resistance of a loop, which turns out to be 20 pi squared times the circumference of the loop divided by the wavelength to the 4th power. Key thing number 2, often you'll use multiple turns in one loop, much like you do for an inductor. So if we had done that, the drawing at the beginning of this video might have, instead of being one circle like this, it might have been n circles. And if that is the case, then the radiation resistance is 20 pi squared c over lambda to the 4th times n squared. So that's a big win, because the radiation resistance goes up with the square of the number of loops. This is great, as long as the total length of the wire is short enough that I is still constant. One last thing that I want to note here is that part 3, the loss resistance increases with n, not n squared. So in general, if you want to make a loop antenna more efficient, you should use more loops, as long as you continue to meet this requirement that the total length of the wire is short enough that the current is still constant. Because remember, current likes to make a standing wave, and it will eventually take on a sinusoidal shape as the length of your antenna approaches a wavelength.